National Fire Protection Association, or NFPA, provides standards for electrical safety in the workplace. NFPA 70E at 70.3 is the standard for electrical safety in the workplace. Section 130.1 subsection states that an arc flash hazard analysis shall be performed to identify employees exposed to arc flash hazards. Section 130.3 subsection D number 1 states that employers shall select and require employees to use appropriate personal protective equipment or PPE based on the arc flash hazard analysis. Section 130.7 subsection states that arc-rated clothing and other arc-rated PPE shall be worn by qualified persons performing tasks with potential for electrical arc flash. NFPA 70E Table 130.7 subsection C number 15 subsection outlines the minimum arc flash PPE category for 480 volt systems. This table considers the working distance in feet. For a 480 volts 208 Y over 120 volt system, a working distance of 4.0 feet corresponds to a PPE category 2. A working distance of 6.5 feet corresponds to a PPE category 3. A working distance of 9.0 feet corresponds to a PPE category 4. A working distance of 12.0 feet corresponds to a PPE category 5. A working distance of 15.0 feet corresponds to a PPE category 6. A working distance of 18.0 feet corresponds to a PPE category 7. A working distance of 21.0 feet corresponds to a PPE category 8. A working distance of 24.0 feet corresponds to a PPE category 9. A working distance of 27.0 feet corresponds to a PPE category 10. A working distance of 30.0 feet corresponds to a PPE category 11. An arc flash hazard analysis should be conducted to determine the specific PPE requirements for each specific breaker location. This analysis should consider factors such as working distance, potential energy available, and specific breaker characteristics. The manufacturer of the arc blast suits may have specific guidelines or recommendations on when they should be used, so it's important to consult the manufacturer's instructions for additional information. The company may also have additional policies or guidelines regarding the use of arc blast suits, and it's important to follow all relevant policies and procedures established by the employer. While safety is paramount, it's also important to find a reasonable approach to PPE requirements. Based on the NFPA 70E table, for most 480 volts breakers, wearing an arc blast suit is not typically required if the working distance is greater than 6.5 feet. However, for situations where the working distance is shorter or the potential energy is particularly high, it may be prudent to wear an arc blast suit. Ultimately, the decision on when to wear arc blast suit should be based on a comprehensive risk assessment that considers all relevant factors and complies with applicable standards and regulations. Performing an arc flash hazard analysis involves several steps. Firstly, you need to collect data about the electrical system. This includes information such as voltage levels, fault current availability, and protective device clearing times. You'll need single-line diagrams and coordination studies to accurately model the system. Secondly, calculate the incident energy. Use software or calculation methods outlined in NFPA 70E to determine the incident energy at various points in the electrical system. The incident energy is the amount of energy a worker could be exposed to during an arc flash event. Thirdly, determine the arc flash boundary. The arc flash boundary is the distance at which the incident energy equals 1.2 calories per square centimeter, which is considered the onset of a second-degree burn. Fourthly, select appropriate PPE. Based on a calculated incident energy, select arc-rated clothing and other PPE that provides adequate protection. NFPA 70E provides tables to help you choose the correct PPE category. Fifthly, document the results. Record the results of the arc flash hazard analysis, including the incident energy, arc flash boundary, and required PPE for each piece of equipment. This documentation should be readily available to workers. Sixthly, review and update the analysis regularly. Electrical systems change over time, so it's important to review and update the arc flash hazard analysis at least every 5 years or whenever there are significant changes to the system. Working distance is a critical factor in determining the severity of an arc flash hazard. It's the distance between a worker's face and chest and the potential arc source. The closer a worker is to the arc, the higher the incident energy they will be exposed to. NFPA 70E tables take working distance into account when determining the appropriate PPE category. Increasing the working distance can significantly reduce the risk of injury from an arc flash. For example, if the working distance is greater than 6.5 feet for a typical 480-volt system, the required PPE category may be lower, potentially eliminating the need for an arc flash suit. Consider using tools and equipment that allow you to increase the working distance. For example, use remote racking devices for circuit breakers or insulated sticks for operating switches. Proper training is essential for electrical workers to understand arc flash hazards and how to protect themselves. Training should cover topics such as arc flash hazard analysis, PPE requirements, and safe work practices. Workers should be able to recognize arc flash hazards, understand the risks involved, and know how to use PPE properly. Regular refresher training is also important to ensure that workers stay up to date on the latest safety procedures. Developing and implementing safe work practices is crucial for preventing arc flash incidents. These practices should include procedures for de-energizing equipment before working on it, using lockout/tagout procedures, and maintaining a safe working distance. Also, consider using arc flash rated tools and equipment such as insulated hand tools and arc flash blankets. Regularly inspect electrical equipment to identify and correct any potential hazards. Look for things like damaged insulation, loose connections, and signs of overheating. Repair or replace any damaged equipment immediately. Maintaining equipment in good condition can help prevent arc flash incidents. Protective devices, such as circuit breakers and fuses, play a critical role in limiting the duration and severity of arc flash events. Ensure that protective devices are properly coordinated and maintained. Regularly test protective devices to verify that they are operating correctly. Upgrading protective devices to faster acting types can also help reduce the incident energy during an arc flash. Arc flash suits are designed to protect workers from the thermal effects of an arc flash. They are typically made from multiple layers of flame-resistant material. Arc flash suits are rated according to their arc thermal performance value, which is a measure of their ability to withstand heat from an arc flash. It's important to choose an arc flash suit that provides adequate protection for the potential incident energy at the work location. Other important PPE includes arc-rated face shields or hoods, safety glasses, hearing protection, and insulated gloves. Face shields and hoods protect the face and eyes from arc flash burns and debris. Safety glasses provide additional eye protection. Hearing protection can help prevent hearing damage from the loud noise of an arc flash. Insulated gloves protect the hands from electrical shock and burns. Regularly inspect PPE for damage and replace it as needed. The hierarchy of controls is a systematic approach to hazard control that prioritizes the most effective measures. The hierarchy of controls consists of the following steps in order of effectiveness. Firstly, elimination involves removing the hazard completely. For example, de-energizing equipment before working on it eliminates the risk of arc flash. Secondly, substitution involves replacing a hazardous substance or process with a less hazardous one. For example, using remote racking devices instead of manually racking circuit breakers reduces the risk of arc flash. Thirdly, engineering controls involve designing or modifying equipment or processes to reduce the hazard. Examples include installing arc flash barriers or using current limiting fuses. Fourthly, administrative controls involve implementing procedures or policies to reduce the hazard. Examples include developing safe work practices and providing training. Finally, personal protective equipment or PPE is the last line of defense and should be used in conjunction with other control measures. PPE includes arc flash suits, face shields, gloves, and other protective gear. By following the hierarchy of controls, you can effectively minimize the risk of arc flash incidents. Coordination studies are essential for ensuring that protective devices operate properly and minimize the duration of arc flash events. A coordination study involves analyzing the electrical system to determine the optimal settings for circuit breakers and fuses. The goal is to ensure that the protective device closest to the fault trips first, minimizing the amount of equipment that is affected by the fault. Coordination studies should be performed by qualified electrical engineers and updated regularly. Labeling electrical equipment with arc flash hazard information is critical for informing workers about the potential risks. Arc flash labels should include information such as the incident energy, arc flash boundary, and required PPE. Labels should be clearly visible and easy to understand. NFPA 70E provides guidelines for the content and format of arc flash labels. Regularly inspect labels to ensure that they are in good condition and haven't been damaged or removed. When working on or near energized electrical equipment, it's important to maintain a safe working distance. The safe working distance is the distance at which the incident energy is below the threshold for a second-degree burn, which is 1.2 calories per square centimeter. NFPA 70E provides tables that specify the safe working distance for different voltage levels and equipment types. Use tools and equipment that allow you to maintain a safe working distance. For example, use insulated sticks or remote racking devices. Lockout/tagout procedures are essential for preventing accidental energization of equipment while it is being worked on. Lockout/tagout involves isolating the equipment from all sources of energy and placing locks and tags on the energy isolating devices to prevent them from being turned on. Only qualified workers should perform lockout/tagout procedures. Workers should be trained on the proper procedures and understand the importance of following them. Regularly inspect lockout/tagout equipment to ensure that it is in good condition. Before starting any electrical work, it's important to perform a job safety analysis or JSA. A JSA involves identifying the hazards associated with the task and developing procedures to mitigate those hazards. The JSA should be reviewed by all workers involved in the task. Workers should be encouraged to identify any additional hazards that may not have been identified during the initial JSA. A job safety analysis or JSA is a systematic process to identify potential hazards and risks associated with a specific job or task. It involves breaking down the job into individual steps, identifying potential hazards at each step, and developing control measures to eliminate or minimize the risks. The primary goal of a JSA is to prevent accidents, injuries, and illnesses by ensuring that workers are aware of the hazards and have the necessary knowledge, skills, and tools to perform the job safely. Here are the typical steps involved in conducting a JSA. Firstly, select the job to be analyzed. Choose a job that has a history of accidents or injuries, or one that is considered high risk. Also, consider jobs that are new or have undergone changes in procedures or equipment. Secondly, break down the job into individual steps. Observe the job being performed and list each step in the order in which it is performed. Be specific and avoid combining multiple steps into one. Thirdly, identify potential hazards for each step. For each step, identify potential hazards that could result in accidents, injuries, or illnesses. Consider factors such as electrical hazards, fall hazards, chemical exposures, and ergonomic stresses. Fourthly, develop control measures to eliminate or minimize the risks. For each hazard, develop control measures to eliminate or minimize the risk. Use the hierarchy of controls, which prioritizes elimination, substitution, engineering controls, administrative controls, and personal protective equipment. Fifthly, document the JSA. Record the results of the JSA, including the job steps, hazards, and control measures. Ensure that the JSA is clear, concise, and easy to understand. Sixthly, review the JSA with workers. Review the JSA with workers who will be performing the job. Ensure that they understand the hazards and control measures and have the necessary training and equipment. Seventhly, implement the JSA. Put the JSA into practice and ensure that workers follow the control measures. Monitor the job to ensure that the control measures are effective. Eighthly, review and update the JSA. Review and update the JSA periodically, or whenever there are changes to the job, equipment, or procedures. Incorporate any lessons learned from accidents or near misses. Benefits of conducting a JSA. Firstly, it reduces accidents and injuries by identifying and controlling hazards. Secondly, it improves worker awareness of hazards and risks. Thirdly, it enhances communication between workers and supervisors. Fourthly, it promotes a safer work environment. Fifthly, it complies with regulatory requirement. Considerations for effective JSA. Firstly, involve workers in the JSA process. Workers have valuable knowledge and experience that can help identify hazards and develop effective control measures. Secondly, be specific and detailed in the JSA. Avoid general statements and provide specific information about the hazards and control measures. Thirdly, use visual aids such as diagrams or photographs to illustrate the job steps and hazards. Fourthly, regularly review and update the JSA to ensure that it remains relevant and effective. Fifthly, integrate the JSA into the company's safety management system. Here are some examples of hazards and control measures that might be identified in a JSA for electrical work. Hazard energized electrical equipment. Control measures to energize equipment before working on it. Use lockout/tag-up procedures. Use insulated tools. Wear appropriate PPE. Hazard arc flash. Control measures: perform arc flash hazard analysis. Wear arc-rated clothing and PPE. Maintain a safe working distance. Use arc flash barriers. Hazard electrical shock. Control measures to energize equipment before working on it. Use insulated tools. Wear insulated gloves. Ground equipment properly. Hazard falls from heights. Control measures: use fall protection equipment such as harnesses and lanyards. Ensure that ladders and scaffolds are in good condition. Provide training on fall prevention. Hazard exposure to hazardous substances. Control measures: use proper ventilation. Wear appropriate PPE such as respirators and gloves. Follow safe handling procedures. By conducting thorough JSA and implementing effective control measures, companies can significantly reduce the risk of accidents and injuries in the workplace.